Swayam Prabha. Digital India. Educated India.
So dear students, in this lecture we'll be talking about polyphase system. So we have studied so far single phase AC circuits where we have a AC source of a specific frequency and the circuit is being energized by that sinusoidal AC voltage source. So now we'll be going to polyphase system. Polyphase system basically described as the two or more than two AC voltage sources which are having the same frequencies, but they'll be having a specific phase difference, which is basically the fixed phase difference which the voltage source will be having with respect to each other. So it is basically two or more than two AC voltage sources with fixed phase difference. Okay, phase angle difference, but the maintaining same frequency. Okay, maintaining the same frequency. So two voltage sources or three voltage sources or even more than that, the different AC voltage sources will be present and these sources will be having a same frequency. So normally we have a two-phase system, three-phase system, but most efficiently the most widely used polyphase system is a three-phase system. Okay, so most widely used polyphase system is three-phase system. Okay, so this is the one of the very important point, like why this three-phase system has come up with a very efficient mode of power transfer or transmission or generation. So that we'll see. So what are the main advantages of a three-phase system? So we can just write the main advantages. Three-phase system. So this phi is basically the representation of a phase. So three-phase system can be written as three-phase system like this. So we are using this phi as a system. So main advantage of a three-phase system. So the first one is for the generation of same power output or the machine which is having some rating. So if we have a three-phase machine or a single-phase machine, then the size reduces in a three-phase case. So in general, three-phase machine, three-phase electrical machine or machine has a smaller size. For the same power rating. Okay, so a smaller size means we are comparing the same power output. Okay, so three-phase machine has smaller size compared to single phase machine for same power. Okay, so this is one main advantage. Size reduces, so the machine will be less bulky or it will be economic approach to go for a same power with a reduced size. So the next is the voltage drop in conductors from source to load is less in a three-phase system. So that is we'll be comparing. So in basically in a case of a three-phase voltage, the power loss will be less per conductor compared to the single phase for the same power. So the voltage drop, we can just write it down as the voltage drop per conductor from source to load is less, okay, compared to again single phase system. The conductor material required to transmit the given power at a given voltage for a specific distance is lesser in three-phase system. Okay, so this is also very qualitative or economical advantage of the three-phase system, which is the conductor material required. So conductor material required for some power transmission, okay, for a given power and voltage over a given distance is less in three-phase system. So this is basically for a transmission case. So that is also very good advantage when we have to transfer a bulk amount of power to the load from the generating point to the load side. So with these advantages, the reason of three-phase system has been chosen, and which is very commonly used in practice for generation, transmission, distribution, and utilization of electrical energy. So now let us see how this three-phase voltage look like. So this is the you can see representation of a voltage where you have phase A, phase B, and the phase C. So this is RYB representation. So red, yellow, and blue. So RYB is normally known as the phase. So how these phase supplies are generated? So basically, when the three identical coils are placed, okay, with the axis 120 degree apart from each other. So suppose there is an electrical machine. So when we'll go to the machine section, we'll discuss it in detail. For time being, you consider something which is rotating is a rotor, and there is something which is known as stator, which are the magnets. So just to show you how the generation is happening, so we have slots where the conductors are kept. So this is one slot. Then we have this slot. Okay. So suppose one of the phase is represented by this. So you can just mark them as axis. Okay. And then it is basically a rotating with the speed of omega, and this is, you can give north or south pole of the magnet. So these coils which are being kept, suppose this is the axis and there is a conductor which is being fitted here and one conductor will be here. Okay, so the next phase, suppose this is A and A prime, then if it is rotating anti-clockwise, this will be B and the B prime, and then will be rotating, then there will be some then we have C and C prime, right? So C and C prime. So this is how the phase are being marked. So VAA prime or VA, in this figure you can see it is given as VM sin omega t, and what is a VB is given VM sin omega t minus 120 degree. So you can see that this is nothing but 120 degree phase shift of these phase A and phase B. Now what is VC? VC is VM. So VM is basically the peak magnitude of this. So and then this will be minus VM. So VM sin omega t minus 240 degree. Okay, so what we see from here is these are the three voltages of a frequency f or omega, which is fixed in all these three cases, but the phase difference is observed as 120 degree with respect to each other. So now if we try to draw the phasors, so suppose we are taking reference as VAA, which is VA here. So we'll start a little low, so we'll just yeah. So now we can have a voltage VA, okay, and the magnitude is VM. Then with respect to this we have to go 120 degree, then we get VC, because this is, and this is VB. So this is basically rotating anti-clockwise direction. So after VA, VB will come. So this is 120 degree in the opposite direction. Similarly, this is 240 degree. So this can be written as plus 120 degree also. So this we can also write as VM sin omega t plus 120 degree. Okay, minus 240 or plus 120 degree is the same thing. So when we write it in a phasor form, VAA or the voltage VA is nothing but V angle 0. Okay, polar form. Similarly, VB is nothing but V angle minus 120 degree, and VC is nothing but V angle minus 240 degrees, or V angle we can give as plus 120 degree. So these are the phasor form of these AC voltages. So we see that VAA leads VBB by 120 degree. So this VAA is leading this VB by 120 degree, and VBB leading VCC by 120 degree. So this is also 120 degree only. So B in this direction leads VC by 120 degree. VA is leading VB by 120 degree. So this is how the phase difference of 120 degree is maintained. So now these voltages are basically represented in terms of a generating windings. So normally if you see the three-phase voltage representation, we have been having like this kind of representation. So only the difference with the inductor and this winding is that we'll be giving this a value of like A prime, where the value generated can be written as V. So this is a winding. So this is basically a voltage source. So this can be represented as Vm sin omega t or V. So this is basically a sinusoidal A and A prime. So when we connect the three phase voltages, we have two different kind of topology of connection. One is star connection, which is also known as Y connection, and another topology is delta connection. Where you see delta connection. So these are the two names of these thing. Okay, so we'll see one by one how these connections are made and what are the condition sources has to take. So when we talk about Y connection, then we have one winding. Suppose we are connecting this way. So this is A, which is positive, and A prime, which is negative, just for the sake of representation. So now from here we have 120-degree lagging of B prime and B, and then we have C prime and C. So this is the basically a Y representation, a star connection, where A prime, B prime, C prime are connected to the same point. So the point where the A prime, B prime and C prime are connected, these points are known as the neutral point, or sometimes it is normally says as only neutral. So this point is basically a neutral. Okay, or also the star point, sometimes some book refers as a star point. So it all means the same thing, where A prime, B prime, C prime are connected, or one of the terminal of the windings are connected to the common point. So when we look at the circuit is this direction, so we have one voltage source here, another source terminal is here, and then we have one more terminal which is coming here. So this is A, B or C. Most of the time there will be like neutral terminal also will be coming, and this is N. So this is basically known as three-phase, four-wire system, because there are only three phases, but there are four terminals, like neutral also is coming. So thereby we have four wires. So this is known as three-phase, four-wire connection, or if it is a voltage sources, we call it as three-phase, four-wire supply. Okay, so this is three-phase, four-wire supply. So the magnitude of all the voltages will be same. So what we can say with respect to the neutral, suppose this is marked as N. Okay, so VAN, the magnitude of VAN is equal to the magnitude of VBN, or with respect to each other the magnitude will be same, which is nothing but VM, not VM, the phase voltage. So with respect to neutral it is given as a phase voltage. Okay, so when we talk about a single phase like phase A, phase B, phase C, with respect to the neutral, then the voltage is phase voltage. So if we try to write the phase voltage in terms of phasor quantities, so VAN is nothing but V phase voltage, VP represents the phase voltage. So where we can write where VP is phase voltage. Okay, so when VP is a phase voltage, we are representing VAN as a phasor quantity, VP angle of 0 degree. Okay, or in case of rectangular form or Cartesian form, we can write P VP angle of 1 plus J0. Okay, similarly if we try to write the VBN, which is the phase B voltage with respect to non-neutral, which is VP angle of 120 degree. Okay, with a negative sign. So what will write this? This will be VP sine 1 minus 120. So we can represent in Cartesian form with the angle of this. So it can be written as minus 1 by 2 minus j root 3 by 2. Similarly, VCN is nothing but V phase angle of minus 240 degrees. And when we try to write this in a rectangular form, we get minus 1 by 2 plus j of root 3 by 2. So these are the three voltages. So this term, you want to write V angle of theta, it is represented at V cos theta plus j sin theta. So this is the polar form and this is the rectangular form. So using this, we have written the polar and the rectangular form. And now what we'll do, we'll try to add all these voltages. Okay, so what are the relationship of the phase and line voltages in a balanced three-phase star supply? So now we'll talk about the balanced three-phase supply. So when we talk about a balanced three-phase supply, means it has to meet two conditions. Okay, so first condition is the magnitude of the voltage should be same. What voltages should be same for each phase? Okay, so this is the condition. So each phase voltages magnitude should be same. And the second is the angle or the phase angle difference. We'll write the phase angle difference. Must be 120 degree with respect to each other. Okay, with respect to each other, each phase. Okay, so these are the two conditions. So already we have assumed here that VAN, VBN, VCN, all the magnitude is same VP. So this is a balanced three-phase supply, provided that the phase angle is maintained in this range 0, 120 and minus 240. So this is known as the balanced three-phase supply. So in case of balanced three-phase supply, we'll see one more small concept and then we'll see what is the meaning of star connection. So now let us add all the voltages. So VAN plus VBN plus VCN. If you add these voltages, what you'll get? So keeping the value as VP angle 0. Okay, so VP angle 0 plus VP angle minus 120 plus VC, which is also VP angle minus 240 degrees. So when we take VP common, so it will be 1 minus 1 plus J0 plus 1 by 2 minus root 3 by 2J plus, oh sorry, this is minus and this is also minus 1 by 2 plus root 3 by 2J. So you see 1 by 2, 1 by 2 and 1 will cancel and this will get cancelled with this. So we'll get 0. It means that VAN plus VBN plus VCN, the phasor sum of all the phases voltages will be 0 in a star connection. Okay. So the phase sequence is same order which voltage pass through the respective maximum values. So let us see what the phase sequence means. So we'll see new term here, which is phase sequence. So we have drawn a phasor diagram We can go and have a look there. So in this case, it is rotating in this direction with the like anti-clockwise direction. So if we try to find out what is a phase, so phase means if you start looking at this point, and after some point you'll be seeing one more phase will be coming up, correct? So what is the phase will come when you are observing at this point? So after VA, we get VB, and then we get VC. So this is phase A, B, C. So this is a phase sequence. Okay, so phase sequence is A, B, C. Now, if you want to see here, A is basically red, yellow, and blue. So this is basically R, Y, B. So this is phase sequence. Okay, so now if we redraw this, so basically if let us write one statement that it is the time order in which the voltage passes through. Voltage passes through their respective maximum values. Maximum values. So if suppose it rotates in opposite direction, so here also you can see, so after phase A, phase B is passing its maximum values, then phase C is passing their maximum values, and again phase A turns up as a maximum value. So this is A, B, C, again it will be A, B, C, like this it will keep on happening. So phase sequence here will be A, B, C or R, Y, B. If the direction gets changes, if suppose it rotates in opposite direction, then it will be phase A, then C, and then B. So after A, C will come, then it will be A, C, B or R, B, Y phase. So the phase sequence will change. So this is still the phase sequence. Now we have seen that the phasor sum of the line voltages is 0. So one of the important thing we have just rewritten in star connection, star or Y we will mention WYE, Y connection, the phasor sum of all phase voltages is 0. So this is one of the important condition that we have seen in case of star connection. Now look at for another topology, which is delta or delta connection, right? Sometimes it is also known as mesh connection because it forms a small loop. So how these windings are connected? So A prime, B prime, C prime. So this is phase A, this is phase B, and this is phase C. So these are basically connected in the form of a delta, which is forming a mesh. So this is known as mesh connection or a delta connection. So this is, and this is, and this is. So this is C, this is B, and this is A. Okay, the positive terminal we have taken. So these are basically the voltages terminal which are coming from a mesh connection. So these coils are connected in the form of a closed loop. Okay, so the connection is such that one's negative is connected to another positive terminal. So one prime, another's non-prime. So the supply lines in delta connection are taken from these junction where the connections are made. So this is phase C, phase B, and phase A. So the magnitude, if we talk about the balance delta connected system. So when we talk about balanced delta connection, basically the system where the voltage supplies are there. So balanced delta connection means the magnitude of phase voltages with respect to each other, which are basically known as the line voltage. So this is basically a line. So this is known as the line voltage. This is line voltage. Why this is line voltage? Because this is between the two voltage terminal. Okay, so VAB, VBC, and VCA. These three voltages will be measurable with respect to each other. These are basically line voltages. Okay, so line voltages are measured with respect to each phase only. There is no neutral in this case. So this is, we can write it as three phase, three wire system. There is no neutral. So when there is a neutral, then there are phase voltages, but here every voltage is a line voltage. So in the case of line voltage balance case, so V line voltage is equal to phase voltage, which is VAB. If you talk about the magnitude, which is equal to VBC, and which is equal to VCA. This is a balance condition. Okay. So now if we want to find out, here you can see the line voltage and the phase voltage is same. Okay, this is the again one important observation in delta connection. What is the voltage which is appearing across the phase? This is phase, right? VP is equal to the line voltages. The same terminal voltage across, these terminal A prime is basically the phase voltage, the magnitude if you take the phase voltage, then it is equal to the phase AB. So VAB is equal to wave phase. So line voltage is equal to the phase voltage. V line is equal to V phase in delta connection. Now calculate the line voltage in star system, which we have seen earlier, right? So VAB, what is VAB? Go to the star connection and see. VAB is nothing but VAN plus VNB. Okay, so VAB is nothing but VAN plus VNB, or VAN minus VBN. This is the line voltage. Now we can write it as VP, angle of 1 plus J0, minus VP 1 by 2 minus J root 3 by 2. Okay, so when you solve this, this is VP, and you get an angle of 3 by 2 plus J root 3 by 2. So when you try to look for this in the form of a polar quantity, so it will become 3 root 3 VP angle of 30 degree. So what we did, we basically took the common and then it will become root 3 by 2 plus j 1 by 2. So from here we can write this form. So this is VAB. So from here what you see, VAB is basically similarly if you try to find out VBC, this will be coming as root 3 VP angle of minus 90 degree. Similarly VCA, it will be root 3 VP angle of 150 degree. So after this, one interesting observation can be made when we draw the phasor diagrams. So draw the phasor voltage in case like phasor diagram of star connection. Okay, suppose like earlier we have taken the phase voltage as reference, so we'll take that as a reference. So this is VA, VB, VC. These are the phase voltage. So line voltage is VAB, where you can write as root 3 times of the magnitude and angle of 30 degrees. So suppose this is the angle of 30 degree and the magnitude is root 3 times of this VP. So this is basically the phase voltage VP. So this is root 3 of phase voltage and the angle is plus 30. We are moving this direction. So this is nothing but VAB. Similarly, you have VBC. Correct. VBC is root 3 times of VP. So the magnitude will be of same length. This is root 3 VP and the angle will be minus 90. Similarly, this will be VCA. VCA is the angle of this 150 degree. So if you see clearly this V phasor diagram, right? So basically this is the negative of VB. So VAN minus VBN is the voltage. Okay, so VAB is nothing but VAN minus VBN. VBC is nothing but VBN minus VCN, and VCA is nothing but VCN minus VAN. So from here if you do, you'll get the relationship which we have covered, root 3 times of the phase voltage.